let's do some circuit math. I'm sure you're shocked to find out that I'm ready to go. Alright, so let's start off with a simple series circuit, one resistor, one pathway to ground. So first things first, let's figure out total circuit resistance, RT, up there at the top. 2 ohm resistor, the only resistor, so that makes our life easy. We have 2 ohms of circuit resistance. Figure out how much amperage is flowing through that circuit. So I'm trying to solve for amperage, so I'm going to cover up the A. I've got 12 volts, I've got 2 ohms, 12 over 2, right? Gives me 6, so I have 6 amps flowing through this circuit. If I wanted to figure out my voltage drop, well, then I would just do Ohm's law again. This time I'm solving for voltage. I know how much amperage is flowing, I know how much resistance there is. So 6 times 2, it's going to give me my 12 volts. Kirchhoff's second law tells me that I have to drop all the voltage as I go across this resistor. It's the only resistance to ground, so it has to drop all of the voltage. That one was too easy, so let's step it up one notch. 2 resistors, both the same resistance value. How do we figure out what the resistance of this circuit is? Well, since there's only one pathway, we just add the resistances together. It's 2 ohms hard here, it's 2 ohms hard here, you just put them together. So we end up with a 4 ohm total circuit resistance. I can plug that into my Ohm's law chart over here. 12 volts of pressure applied through voltage, 4 ohms of resistance, so that's going to limit my current flow down to 3. And again, we're just covering up what we don't know. 12 is over 4, so 12 over 4. Now I want to figure out how much voltage is dropped across each one of these resistors. Again, Ohm's law. Thank you, Georg. So I've got a voltage that I'm solving for. I've got 3 amps flowing through this circuit, and I have that first resistance is 2 ohms. So side by side means you multiply. So 6 volts dropped there. And we can say, there's still 3 amps flowing through here, so again, it would be 6 volts dropped. Alright, pretty straightforward so far. I'm using easy numbers, but it's because I just want to understand the theories of things. It's not really important that we're able to do like real advanced calculations or anything like that. Let's step it up another notch. And now I've got 2 different resistance values, so the amount of voltage dropped across each one of these is going to be different because the restriction is a little bit different. The bigger resistance should drop the majority of the voltage. Let's see if the math works out there. Again, I need to find total circuit resistance, so I'm just going to add them. 2 plus 4 gives me 6 ohms. Total circuit resistance. Now I can plug in my numbers to figure out my total current flow through this circuit since there's only one path, 12 over 6. I'm sure some of you are already there. 2 amps flowing. And now I want to figure out voltage drop across this first one. Hello, ohms. So I've got 2 amps. I've got 2 ohms. 4 volts dropped. Let's do this next one. I'll do it over on this side to keep things separate. Ohm's law again. I'm solving for voltage. I know I've got 2 amps flowing through this circuit. 2 amps. I've got a 4 ohm resistor based off of what my circuit is telling me. 4 ohms. And if I put them side by side, 2 times 4 equals 8. All right, and there's another way that we could have gone about doing this. We could have just taken that 4 volts that was dropped to begin with and done 12 minus that 4 volts, because we know we have to drop everything. That would have given us 8 as well, which totally fine way to go about it. Just we're going after the same theories in opposite directions. If this was a real circuit and I could use a meter, here's my little meter. Bought this at Home Depot. It was like 20 bucks. This meter is capable of doing almost all the stuff that we would do in this class. You might miss out on a couple of the activities we do in the lab as far as like testing a thing or another thing, but for 20 bucks, this does a whole bunch. I often leave my good meter at work, and so I was doing some electrical work around the house, and I just wanted to know if something was going to zap me or not, so this did more than enough for that. When I go to figure out what setting, since this is manual ranging, 20 volts DC, you see the little straight line there versus alternating current that's up there. So it's a 12 volt circuit. 20 volts is the closest thing. This is 2000 millivolts, which is only like 2 volts. So 20 volts is closer than 200 volts and 2 volts, so I'm going with 20. I want to see my reading, and I'd like a decimal point if at all possible. So if I use this meter and did a voltage drop across this circuit, red lead on the power side, black lead on the ground side. If I get them mixed up, I'm just going to see a negative sign, so with direct current it makes that pretty simple. But I would see 8 volts displayed on the screen because it's telling me what the difference is between here and here. And on this circuit, I've got 8 volts here, and I've got nothing left down here at the bottom because it should be all gone. So it would display 8 volts, and I would see that I had an 8 volt voltage drop. Here, however, I would also see 4 volts displayed on my meter, but the math that it's doing this time, and it's not really doing math, it's just sensing a pressure differential, but the math that's really happening is I've got 12 volts here, and I've got 8 volts right here, and so the difference between 12 and 8 is 4, so 4, 8, 12, okay? This bad boy out of the way, and move on to something more interesting, because I'm sure you're like, Casey, this is so boring, I've done it a million times, and series circuits are so easy, why are we doing this? Well, it's because circuit math is great. Alright, parallel, this makes things harder just because fractions are involved, and so that's enough to make some people just want to call the whole thing quits, right? So this time, guess what I'm going to do first? I'm going to solve for total circuit resistance. I've got two 2-ohm resistances, so some of you already know a shortcut to get through this. If the resistance value is the same on both legs, we just divide that resistance value by the number of legs. So here I've got 2 ohms, I've got 2 legs, so I should come up with 1 ohm of resistance. 2 divided by 2 is 1. In this case, I'm just going to go on with the tried and true method that works no matter what. And I need to do 1 over the first resistance, which is 2, plus 1 over the second resistance, which is 2. And because the denominators on the bottom here are the same, I can add up my numerators on the top. So that comes to 2 over 2. And to make sure that we're keeping good habits, we have to make sure that we get the reciprocal of this. That means I have to flip it over. So 2 over 2 flipped also is 2 over 2. And that reduces down to 1 ohm, which is what some of us were expecting to see. It's just good practice. Let's just always do that because it always has to happen. Now that I know my total circuit resistance, I can figure out my total circuit amperage, AT, right? So I've got 12 volts pushing through 1 ohm of total circuit resistance. I've got 2 pipelines of 2 ohms. So I've got definitely the ability to flow more than what just one of these would have because there's 2 of them. It makes sense. 12 over 1. This is some high class math right here. 12 over 1, 12 amps. So right here, I would have 12 amps flowing. When I get down to this junction, Kirchhoff's first law is that current flowing through a junction will split. and the sum of those currents will add up to my source current. So if basically what I have here is if I follow this down, I've got 12 volts, no resistance. So really I just have 12 volts here and really 12 volts here because I haven't dropped any of it yet. That's very, very similar to where we started. Right here, right? 12 volts, 2 ohms. So let's see if it follows along with what we expect to have happen. 12 volts, 2 ohms. We'll do another little Ohm's law chart over here. 12 volts, 2 ohms. How many amps? Cover the thing up. 12 over 2 gives me 6 amps. Definitely going to be the same over here as well, 6 amps. So now I can use that to figure out my voltage drop. Any guesses on how much voltage we're going to drop? We've only got one resistance, so we almost don't even really need to do the math. And by almost, I mean we don't have to do the math. We have 12 volts here, one resistance, guard and ground basically. I should drop all of this before I get there. But ohm is going to always take us where we want to go. So I know I've got 6 amps flowing through 2 ohms. Right, 6 amps through 2 ohms. How much voltage do we drop? 6 times 2 gives me 12. Hey, it makes sense. And you know this other side is going to act exactly the same way, right? If 6 amps flowing through 2 ohms does one thing, well, I bet it's going to do the other thing too. When we come back down here, completing Kirchhoff's statement about currents recombining again to their source current, then I've got 6. That comes back to 12 amps, and that's headed towards the battery through the body or the frame, whatever part of the metal components of our vehicle. But first law here of Kirchhoff's is currents will split, but it's always going to add back up to our source current. Conservation of energy and whatnot. We don't just destroy energy, it just changes. Let's make this a bit more exciting now. Now we have a parallel circuit with 2 legs of different resistance. So, I mean, what more could you possibly ask for in life? What do you think I'm going to do first? Give you time to think about it. Then more time than what you wanted me to give you to think about it. And then I'm going to tell you we're going to do total circuit resistance. Who would have guessed? So again, 1 over my first leg's resistance. So that's 3 in this case since there's only one resistor. 1 over my second leg's resistance. And I'm adding these together again. But this time my denominators are not common. That means I can't add them. This is apples and oranges. Alright, so I need to make my denominators the same, and it looks like I could just double this one and get 6. So thank you, easy numbers. That makes life easy. So I'm going to multiply this whole fraction by 2. So 2/6 is the exact same thing as 1/3, right? 1/3 is just simplified all the way down. So 2/6 plus 1/6 equals 3/6. Have to find the reciprocal. So 6/3. Oh, that's easy. That is definitely 2. So my total circuit resistance is 2 ohms. Alright, life is good. Now I want to figure out my total amperage. So I'm going to take my 12 volts and my 2 ohms, and that's going to give me an amperage of 6. That all makes pretty good sense. So 6 amps. I want to figure out how much amperage is flowing down this circuit. Honestly, the easy thing to do is just to remember the fact that there's 12 volts here, 12 volts here, no resistance in between my source and my leg, so we'll just turn these into little series circuits and make the whole world feel a lot better. If I do my Ohm's law chart, I've got 12 volts, 3 ohms, 12 over 3. Oops, I gave the answer away. 12 over 3 gives me, I'll write that again just because it's not very clear. 12 over 3 gives me 4 amps flowing through this circuit. And how much you want to bet that 2 amps are flowing through the other, right? If this is going to split but equal, we've got 4 over here, it's got to be 2 over there. Still take the long road. 12 volts, 6 ohms, 12 over 6. Hey, look at that. Making it happen. So 2 amps down this one. If I want to figure out my voltage drop across this resistance, well then I just need to know that I have 4 amps, 3 ohms, 4 times 3 equals 12 all day long, and so does 2 amps. We've got 6 ohms. Whoa, 2 times 6. That also equals 12. How convenient, because we really needed them to make physical science make any kind of sense whatsoever. So 12 volts dropped across each one of those. So let's write all this down. So I got 4 amps, 2 amps, 12 volts, and 12 volts. Always make sure that you label your work, because 12 doesn't mean the same as 12 volts, right? It could be 12 potatoes, it could be 12 tomatoes, it could be 12 tacos, which I would much prefer the 12 tacos over the other 2 options. All right. Getting close to the end, but not quite there yet. Now all of a sudden we've got a parallel circuit with 2 resistances on one leg, one on the other. So we need to figure out total circuit resistance. But I don't even know the resistance of this leg. So let's add a couple things here to our list. R1 and R2. What's my resistance of leg 1 here? 2 plus 2 equals 4 all day long. That one's easy as 4. It's the only one that's there. So now all of a sudden both my legs look like they're the same. So that's pretty cool. Let's figure out my total circuit resistance now. 1 over 4 plus 1 over 4 equals 2 fourths. Got to do the flip-flop, so 4 halves equals 2 ohms of resistance. Now we can plug that in to figure out that, again, we have 6 amps of current flow here. And now I want to figure out how much is going to go each way. Again, no resistance between here and there, so I'm just going to turn these both into little series circuits. And this is what's happening all over the car. We've got a fuse panel, and each fuse powers up a few different things. And really what we're doing is like, hey, my power window motor has 12 volts applied to it. And then the fuse next to it might be powering up some of my interior lights or something like that. And those are run in series because they don't have to be that bright, and blah, blah, blah. So it's very common to see this kind of stuff. And this is really the way that the whole car is put together. It's just one big, giant parallel circuit because we just have one battery in there. So every single thing that works off of that battery is in parallel with the other circuits. If I've got 12 volts here, and I've got a combined 4 ohm resistance here, that gives me over 4 ohms. 12 divided by 4, right? 12 over 4, we can start doing this now. Gives me 3 amps of flow. That'll help with the voltage drops here in a second. 12 volts, 4 ohms. 4 ohms. 12 over 4 is going to give me, oh wait, hey, how about that? 3 amps of flow. So we can already guess, yeah, this is the only one that's there. Must have to drop all 12. But I've always been a sucker for some good old circuit math, so let's do it. 3 times 4 gives me 12. So there's that reassurance that math is still math. And then over here, we should start to be seeing that I'm going to drop half and half of the voltage because I have two resistances and they're both the same. So each one, since there's only two, is going to drop half. But we can prove that too again. Solving for voltage. Got 3 amps. I've got 2 ohms. 3 times 2 equals 6 all day, every day. Alright. Throws that up to 12. So there's our completed circuit math for this one. Doing great. Masters of our own reality. But now, here comes, dun dun dun, the series parallel circuit. What on earth are we possibly going to do to solve this one? So, this one here, if I'm going to go for total circuit resistance like I always seem to, what I need to do first is, figure out what my parallel circuit's resistance is. The series part of this circuit, well, that's easy. It's got 1 ohm of series resistance, but how much resistance is there here? So I have 2 and 2, so I'll do 1 over 2 plus 1 over 2 equals 2 over 2. We're going to go back to the whole beginning and do the flip-flop business, even though it's the same. It's just good practice. So 2 over 2. That gives me a resistance for this section of 1 ohm. That'd be this parallel section right here is 1 ohm. Alright, so I'll draw a circle on it so it's encompassing that parallel circuit. 1 ohm, 1 ohm. Well, now we can start to treat this thing like it's a very, very simple circuit. And we have a total circuit resistance of 2. There's our 2 ohm resistance written up there. How much current's flowing through the whole thing? Well, I don't know. 12 volts, 2 ohms, 6 amps, right? Cover up what you don't know. 12 over 2, 6. So there's our 6 amps. And then I want to figure out how much amperage is flowing through each leg. Well, let's just turn this back into Old Faithful. Oop, I can't do that, can I? Got a resistance here all of a sudden. Okay, so this starts to become a little bit more complicated. How will I figure out how much voltage there is at the top of each of my parallel circuits? Voltage drop is the answer, my friends. So I've got a 1 ohm resistor, and I know 6 amps has to flow through that because I just solved for total circuit resistance. So let's do it. I've got 6 amps flowing through 1 ohm, gives me 6 volt drop. So 6 volts drop just like that. Now, some simple math, 12 minus 6 is 6. Each one of my parallel legs is only supplied with 6 volts now because this greedy 1 ohm resistor just gobbled up half of it. It kind of makes sense. If this is 1 ohm combined and this is 1 ohm by itself, well, then each one of them is going to drop half the voltage. So here we go. Now I've got 6 volts, 2 ohms. How much amperage is flowing through each of my circuits? 6 volts, 2 ohms. 6 divided by 2 equals 3. So 3 amps. Now I made it small. It's a little crowded in there. So my apologies, but I'll write it up here for you as well. This side's exactly the same. So unless you guys really want to do some math, I'm just going to, believe that both sides are the same. Now that I know how much amperage is flowing through each one of these, and really I could have intuited this anyway, I'm dropping 6 volts here. This is the only resistance left on this circuit to ground, or this leg of the circuit to ground, so it should drop the rest, which is 6. Same thing over here on the other side. Oop. It sounds like the males here. Boomer is very excited. I think he's getting food pretty soon, so he might just be waiting for that to show up. But let's do some Ohm's law to prove it. Draw right here in the middle of everything. So here I've got a 3 amp flow through a 2 ohm resistance. 3 times 2 equals 6 all day long. So 6 volts is dropped here. So we'll fill in the rest of this chart here. Okay. I hope that this stuff is helpful when you go through and do some review, because the quiz this week will be really basically all of this kind of stuff. Alright, and then the last bit, I know you're sick and tired of listening to me talk. It's been a while, I'm sure you got some snacks you gotta go eat, or I don't know, some push-ups to do because you're self-quarantining and social distancing and all that kind of fun stuff, but last one, life will become a little bit easier after this, I promise. So, do you have any guess on what I'd like to do first? Casey, you want to solve for total circuit resistance? How did you know? I am shocked. You guys are amazing. Alright, so let's do this first parallel circuit too. This is really a series circuit and a series parallel circuit. There's a little bit of everything all put together. We have 2 parallel sections in series with one another. So you could call it series parallel, parallel series. I don't really care what you call it. It really looks like just a series circuit to me, but we'll see. We'll all see that together once we get to the end. So let's figure out what my resistance here is, and because I'm a nice guy, it's obviously going to be the same down there on the bottom. So I've got 1 over my first resistance, because that's the way that this game is played, plus 1 over my second resistance equals common denominators. Man, what a nice guy. Common denominators, so 2 over 2. Still going to flip it around because that's what you do. 2 over 2. So that gives me a total resistance for this section of 1 ohm. And that's going to be true down here too, right? We have the same thing, 2 2-ohm resistors in parallel, so each one of them is 1 ohm. And so now we can really start to think about the circuit like this. We've got a 1 ohm resistance and a 1 ohm resistance. And I'm going to let you take that in for a couple seconds. So 1 ohm, 1 ohm. They're both going to act the same. And it wouldn't even matter if these 2 resistance values were different. Okay, if I had 2 different resistors, I did the math, it added up to 1 ohm. Each one of these legs is going to act like just a single 1 ohm resistance. The amount of current flow that goes through them will be a little bit different, but it will add up to be the same as just if there was a 1 ohm resistor in there. I know, I'm blowing some minds here. It's outrageous. Alright, so let's do some math, because who doesn't like math? So I got 1 ohm, 1 ohm, basically in series, so we would just add those together to come up with a, sorry, I'm losing my bits. So that would add up to a 2 ohm total circuit resistance. Okay. Total current flow through this circuit, well, I don't know, 12, 2, 6, right? Cover up what you don't know. 12 over 2 is 6. All day, every day. And because these are each the same, we can start to intuit that I'd have 3 amps and 3 amps going here. And we can prove it down here by saying, how many amps do we have? Well, if I'm doing, if I've got, well, actually that's a little bit complicated because we have to think about the entire circuit in context. So we would really need to start visualizing it like this. And we would say, well, I've got an RT of 2 ohms, and I could plug that in. So I'd have 12 volts, 2 ohms, 6 amps. And we'd know that 6 amps is flowing through here. 6 amps is flowing through here, and we'd actually have to figure out voltage drops first, which if we do that, 6 amps, 1 ohm, 6 times 1 is 6. So I have 6 volts dropped. Knowing that I drop 6 volts across that would help me figure out my amperage. So if I know I'm dropping 6 volts here, then we'll go back down here, my 6 volt drop, my 2 ohm resistance, 6/2, would leave me with that 3. So once we get to this kind of stuff, you have to start thinking about the circuit really in its entirety. You can't really just like putz around like what we've been doing with some of these things. You have to get your thinking cap on and really consider what's happening in the entire circuit before you can just cherry pick different sections of the circuit. But drop 6 volts, and that would be 6 volts across this entire resistance, leaving me with 6 volts left. And so common sense tells me that I should drop 6 volts across the next section. Granted, it's exactly the same as what we just did, so it should act the exact same way as well. So I only put 2 voltages here because really voltage drop 1 is here, voltage drop 2 is here. So 6 volts, 6 volts. And since we figured that out, now all of a sudden we have a pretty good idea of how my amperages were working. We figured out through Ohm's law real quickly about the 6 amps. And then using some of our real thinking cap skills, we came up with 3 amps through each one of the different legs. And that's going to separate 3, 3, recombine to 6, separate 3, 3, recombine to 6, and then head back to my battery again, because battery flowing out of the amperage flowing out of the battery is amperage flowing back into the battery. It's a closed loop. Nothing gets left behind. We drop some pressure as we go, but the actual physical electrons that leave that battery have to show back up inside the battery. Now, I showed you this image, and this is my preferred way, personally, to think about more complicated circuits like this one up here. I like to figure out all the bits and pieces, and then just like simplify it down as much as possible. Life's hard as it is. Why are we going to make it more complicated? This is the way that we should think about this, because this is in series with this. Now, this is often mistaken for the way that someone should think about this circuit, right? I've got 2 parallel circuits, 2 and 2. And so oftentimes people think, okay, this is how I should approach the situation. No, that is wrong. That is not what was just shown to you. That is not this same circuit that's right here, okay? This would have a leg resistance of 4 ohms and 4 ohms, okay? It's not the same. The amount of current flow that gets limited here is gonna be different. The way that voltage drops as you go across it, it's gonna be different, okay? So just do yourself a favor. The big stance is like, some of you will be like, well, I'm seeing like 3 volts and I'm seeing, or not 3 volts, I'm seeing 3 amps maybe flowing down each one of these circuits and blah, blah, blah. The real problem doesn't come up in just the basics of circuit math. The real problem comes up when we actually start to try to troubleshoot this problem, okay? Because if I cut this wire right here, then current's not flowing through the circuit whatsoever. If I cut this wire right here, well, then all of a sudden current can flow through that other leg of the circuit. So even though you might be able to reconcile some of the math, the actual physicality of the circuit, the way that it's going to act on a vehicle or on our breadboards or what have you, we won't be able to approach the two the same way as far as diagnostics go. So just be real careful about this stuff. Really think about how circuits are drawn, and you will be in great shape. I know that a lot of you really took to the circuit math when I had you in the 150 class this fall, and this is just because it's been months and months since we've gotten to do it together. So I'm never shy when it comes to circuit math. Always interested in getting my my hands dirty, as we say. Okay, so here we go. This is the last that I'm going to do an intensive on circuit math. You're not going to be able to get away from listening to me talk about it when we look at wiring diagrams, but that's the whole reason why we go deep into it right off the bat anyway, right? So I miss you all. I hope you're well, and hope you enjoyed.